Hey everyone, so in this video we're going to be looking at and kind of going over the thinking and explanation for these kind of intro problems on work and calculating different types of energy that were from page 174 in the textbook. And so for this first one, and I have kind of all the math already done, so feel free to pause this when necessary to kind of fill in a little bit as needed. But how much work are some movers doing horizontally pushing a 150 kilogram crate some distance across a rough floor without acceleration? So rough floor, that means that we do in fact have friction, of course, but it's not accelerating. So that means that the push force forwards and the friction force backwards are balanced. Since there's no acceleration, these two forces are equal, and we're given a coefficient of friction. And so we need to find the work done by the movers, which is the force of them pushing times the distance. We know the distance is 12.3, so what the heck is their force? Well, we were kind of secretly given a hint as to how we can find this force that they're pushing with, because their push is equal to friction. So we can find, if we can find friction, we can find their push force. We can plug that into this equation in blue. And so looking up on my equation sheet for kind of our AP Physics 1 course, friction is mu times the normal force. We were given mu, so I need to find the normal force. Well, the normal force is matched by gravity. We're not having this crate like accelerating up into the mesosphere. We're not having this crate accelerating through the mantle of the Earth. And so I can swap out the normal force with the force of gravity, which we know we can then rewrite as m times g. So we know mu, 0.7. We know the mass, 150 kilograms. We know g. I can plug all three of these in. I know my friction force. That friction force is my push. So I can swap that in for my force that's actually getting pushed, or my parallel force. So I use that as my force, I times it by d, and I find that my movers have done this much work, kind of written in scientific notation. Next one, how high? So we're really kind of being asked for what is y. That's really what's being asked here. What is y for a rock that has this mass if it's thrown straight up by someone who's done this much work on it? So now we know the energy, essentially, and we're being asked how high. So we know the energy that's put into it. And since we can't have this energy poof disappear, the amount of energy that was done on it must be the energy that the rock has at the top, at kind of its maximal height. And so at its maximum height, it does pause for like an instant at the top. And so we know, since that's the case, there's no kinetic energy at the top, so it's all potential. So I can essentially go ahead and say that, oh, my potential energy depends on the mass and g and the height. We know the energy is this 115 joules. We know the mass. We know what g is. I can just do some algebra, solve for y. Once I have it kind of solved algebraically for the distance it's traveled up, that's my delta y, how high up it's gone. You could just go ahead and call this y if you want, and just assume that we call the bottom where it is 0 for the height. That totally works as well. But once we've kind of done that, we can just plug in. We know the energy, we know the mass, we know g, so we can find that it has gone up really, really freaking high, actually. So it's like definitely like, I don't know, 120 feet or something like that, vertically up, for this rock that's, I don't know, a little under a pound. And so what is the minimum work? This is kind of a challenging question, because this is not an isolated question. These two questions above were kind of isolated, or this one at least is just a pure kind of energy question. This first problem required some knowledge of like unit 2 on forces and friction. We had to kind of do some throwback. And this third question is doing even more of that. What is the minimum work needed to push a car with some mass, some distance? We know d, we know how far it's going. It's going up an incline, though. So we have this incline plane problem. So hopefully we read this and go, boom, I have to draw my incline plane. I have to draw the car. I have to draw the free body diagram on it, where I'm showing gravity going down, and then I break gravity up into a component that is perpendicular to the slanted surface itself. There's a 90 here, essentially, right? And then there's some part that's parallel, and it's parallel to what? Well, it's parallel to the slant itself. These are pointing parallel to each other, is kind of the idea when we solve these problems. And so we know the angle and we know the distance kind of up the slope is 300 meters. So essentially, we kind of know the hypotenuse, we know the angle. If that's the case, I can find my vertical height here. Um, and it says, what's the minimum work? And in part A, we are to ignore friction. So essentially, I don't know how you're pushing a car uphill with no friction. I don't know how you're walking up it, right? But if somehow, I don't know, you had some grippy boots or you have magnetic boots or something, and the car is like on buttery smooth wheels or something, we can then ignore friction. And so, with that being the case, there's no friction for you to fight. And so, there's no work that you have to fight for friction. Really, the thing that you're having to overcome is this parallel component of gravity because you're pushing it up the slope and it wants to pull it down the slope, correct? And so, really, what we can do here is if you find the force parallel and you know the distance, you know the work that the parallel part of gravity would do bringing the car down the slope. And so you have to do at least that much work. You have to overcome at least that much. That's one way to approach it. Um, and so really what I had to do then is I used sine. Sine would be the parallel part over the force gravity. We know the mass, so we can really easily use m times g and get force gravity. So force gravity times sine of the angle gives us this parallel component of gravity. And so that is the thing that we're having to overcome. And so that is my parallel force. So I swapped out for the parallel force. We know d was this 300 meters. I just multiplied those two and I got that it's like this many, and this is actually incorrect. It should not be newtons. It should be joules of work. I apologize about that. Now, here's a different way you could have approached it. You could have looked at this and said, hey, there's no friction that we're having to overcome. It's really essentially just taking the car from down here and moving it to up here. You could have then said, well, wait, the distance isn't this 300 meters. The distance is whatever the heck y is. And the force that I have to overcome is gravity. If you found that y height and you found the force of gravity, you could have done this force of gravity times y, and we should actually get the same exact answer as we had here. And so I've written that down. I've actually done the work for it, and it does work out. It actually gives you the same exact answer. It totally does work. If you go ahead and you just find this y value instead, you'll actually get the same exact thing because that y height would be 90 meters, and you would do 90 times this, and it will actually give us the same exact answer, which is kind of neat. And what that tells us is that moving at this horizontal distance doesn't take any work because there's no force you're having to overcome sideways, essentially in this x direction. You're just overcoming really gravity every little bit that you move it up the slant here. Now, in part B, though, it says now what's the minimum work if there is in fact friction, and the coefficient of friction is 0.25. And so approaching it the way we did originally for this here, now there's some friction I have to overcome. So really, friction is acting down the slope, and the parallel force is acting down the slope. So if I can find those two forces and add them together, I will know then the total force going down the slope. And I can multiply that total force times d, and that will give me this new work value. And the work should be bigger than this because we're having to overcome, well, now friction, of course. So to do that, I've redrawn the picture. We have to overcome the frictional force and the parallel force to kind of move the car now. And we already know the parallel force. We've all found that earlier. Now, kind of throwing back to our unit 2, we know that friction is mu times the normal force. But in this case, the normal force is being opposed by the force parallel or the force perpendicular. They kind of oppose each other. If force normal was greater, recall, that means my kind of car would be leaping up into the air, or if the perpendicular force was greater, the car would be actually crushing through this incline and like accelerating into the mountain or hillside, and that's nonsense. So really, these two are equal. So I can swap out the normal force for the force perpendicular and just rewrite it this way. So I need to find the perpendicular part of gravity then. Well, looking at my little triangle down here, If sine gave me the parallel part, cosine will give me the perpendicular part. So I used cosine. I kind of just did some trigonometry and algebra, and we get just m times g times cosine of my angle gives us the perpendicular force. We were given mu way up above here, 0.25 for mu. So with that being the case, I can now plug directly into my friction equation, mu times force perpendicular. So mu times force perpendicular gives us the force of friction. So now we know the frictional force down the slope. We know force parallel down the slope. So we know the two forces that are both going downhill. So really, I can add these two together. And when I add those two, I get 5,200 newtons. So the total downhill force then is kind of this sum of friction and the parallel, because they're both going downhill. That's the total force that I have to overcome now in this new situation to move the car up the slope 300 meters. So I now know this new force. I just need to multiply by the 300 meters, and we get this whopping number of joules here. And so we must at least match or exceed this work done. If you match the force, the car actually wouldn't be going anywhere. You just have equal and opposite forces up and down the hill. So if you went like 1 joule over this answer, then the car would start going up the hill. If you're 1 joule under, the car would start slowly creeping down the hillside, essentially. All right. So now number 11 is this helicopter. This is a great one because we looked at some helicopter questions back in Unit 2. We're now kind of looking at it in terms of energy. We want to find the force needed, the force required to give a helicopter of mass m an acceleration of 0.10 g. So this is kind of odd. They gave us no number for the mass, and they kind of gave us a number for the acceleration. We can multiply this 0.10 by 9.8. And we could get a number for it. And then part B is saying find the work done by this force as it moves up some distance h. So again, they didn't give us a real number. So in terms of this, looking at what's just going on, we have a helicopter, and it says it's accelerating upwards. So no matter what, we're not looking at any math, no equations. That means the force of lift, or maybe you called it force propeller or force thrust, whatever you wanted to call it, the upward force must be bigger if the helicopter is accelerating up, right? So there must be a net force going upwards, all right? And knowing from Unit 2, net force is equal to m times a. And I used big M because they called it big M. Now, looking at our given kind of circumstance, the situation of this problem, we see that the net force is, well, the lift force, that's up, that's the force in the positive direction, minus the force of gravity. And this is only because I am assuming that positive is up. If you chose to say that positive is down, well, then you'd have positive gravity and negative lift because you'd be flip-flopping the directions. But most people don't do that unless you're just trying to, I don't know, be extra witty and sharp or show off or something. So with that as kind of what we have now, we can plug in ma for the net force because F net is ma. So I plugged in. We can plug in m times g for the force of gravity. So that's all I've done. We also were given an a value. We were told a is 0.10 g. So I rewrote this again with now just 0.10 g. So now I have m times 0.10 g equals force lift minus m times g. Well, I have mg on the right, and I have like 0.10 mg on the left. I can combine those. And so I'd add mg to both sides, and I get 1.1 mg equals the lift force up. So that's the force that's required. And it's kind of weird. Maybe this felt like it wasn't quite finished. Maybe this isn't a very satisfying answer because we weren't given numbers, but you could be told any value for the mass of a helicopter, and you'd be able to find the force needed to make it accelerate up at this rate is really kind of what it means. We've solved this infinitely many times now because you could have any helicopter mass. It could be a small one, it could be a huge one. And so that's why this is our answer. Now, when we're trying to find the work done by this force, it's pretty easy. It says the helicopter moves some distance h upwards. Well, work is force times distance. We know the lift force, so I plug this in for the force, and the distance they call it is h. So I just have to plug in this lift force times h. So I just have 1.1 mgh. So you could have any massive helicopter and any height, and you could then just plug in the numbers and find out how many joules of work it would actually take. All right. And the last one is, in my opinion, the easiest. Room temperature, some oxygen molecule with a very, very, very tiny mass of 5.31 times 10 to the negative 26 kilograms has a kinetic energy of about this many joules, a very tiny amount of energy because it's a very small thing moving. But it's asking, how fast is this moving? Well, we were given the kinetic energy, we were given the mass. If you look at kind of our kinetic energy equation, we know the kinetic energy, we know the mass, we know everything except V. So this was really, can you do some algebra and get V alone correctly? And then can you just plug in the numbers and do like scientific notation well on a calculator? And in the end, you get that it is going 484 meters per second, which is actually screaming fast, I will tell you. It actually is, I'm trying to think right now. This on a, let me see this on my calculator here. That's actually a little over 1,000 miles per hour. So a typical oxygen molecule in your house is moving at 1,082 miles per hour. So that's it for going over these. Let me know if you have any questions, anything I missed.